And with that, good morning, everybody, and welcome back to Calc 1. Plan for today is I have a quiz ready for you on Standard 4. Then we're going to do one last example from Standard 4, one that I think I'd like to kind of talk about as a class because it's a bit tricky. And then we are going to jump into Standard 5, start talking about properties of derivatives and how we can start evaluating derivatives a little bit easier than this scary limit definition that we've been working with for the last couple classes. I've got my usual office hours next couple days. Today at 11 and at 2. Tomorrow at 10 and at 1. No new homework. But don't forget that you do have a homework set due tonight. So, where do they put mathematicians who commit crimes? They put them in PRISM so that they can be with all the other convex. Okay, and with that, I'll go ahead and pass out today's quiz. Standard quiz rules apply. So one side. Have fun.
Two granola bars. That was your favorite.
Be back in just a second.
Give me an x is equal to -1.
I mean, interpret it how you will. But that's another way to interpret it, yes.
Okay.
We'll go ahead and take a few seconds to finish up your thoughts. And pass your quizzes in, please. Pass your quizzes in, please. Alrighty, so when we last left off on Monday, we had defined the derivative function and started to look at a few examples of how we can actually compute the derivative by taking the average rate of change from x equals a to x equals a plus h, and then taking a limit of that expression as h goes to 0. So I'd like to look at one more example as a class before we kind of move on to our next standard, where this last example is similar to the square root example we had yesterday, going to have a little bit of a wrinkle to it. And specifically, that is going to be, I'm going to take the function f of x equals 1 over 2x plus 3, and I want to find f prime of 3. So in other words, we have this function, f of x equals 1 over 2x plus 3, and I want to find the instantaneous rate of change of this function at the point 3. So I'm going to go ahead and set this up. And f prime of 3 is going to be a limit as h goes to 0 of f of 3 plus h minus f of 3, all divided by h. Same setup that we usually do, replacing a here in our usual formula with 3, since at x equals 3 is the point we want to calculate the derivative. And now, what is f of 3 plus h going to be? So for this particular function,
Would it be 1 over 6 plus 2h plus 3?
yeah, it's going to be 1 divided by the expression 2 times 3 plus h plus 3. In other words, the expression we get from taking our f of x and replacing this x here with a 3 plus h. And similarly, f of 3 is going to be 1 over 2 times 3 plus 3. All divided by h. Compound fractions, everybody's favorite. So, question. Is it okay if we just plug in h equals 0 at this point? Why not? Yeah?
You can't have 0 in the denominator.
We can't have 0 in the denominator, and I think if we plugged in 0 for h, we'd also get a 0 in our numerator here. Because if we remove this plus h, these two terms would be the exact same, so they'd cancel out. Well, we can't plug in h equals 0. I also don't see a nice, easy way to factor out an h from our overall numerator. So instead, I think the best thing to do will be to simplify what we have first as much as possible. See if something nice happens. So in our first term, we can distribute this 2 through to get 6 plus 2h plus 3. So I think that'll give us a 1 over 2h plus 9. And here, we'll get 6 plus 3 in the denominator, so that'll give us a minus 1 over 9, all divided by h. Well, fortunately, nothing's really canceling out very nicely. So We can't just simply factor out an h from the top and bottom and cancel it out like we were with the quadratics that we looked at yesterday and the one on today's quiz. So something I would like to do is, since fractions within fractions are scary to me as well as to you, I'm guessing. If not, then I tip my hat to you. I'd like to combine these into a single fraction somehow. Because if we can combine 1 over 2h plus 9 minus 1/9 into a single fractional form, it's going to give us some expression that I think will be a little bit easier to work with, rather than having one fraction over h, one fraction minus another fraction all over h. We can have single fraction all divided by h, then I think this will be a nicer expression. So what can we do if we wanted to combine these two fractions, 1 over 2h plus 9 minus 1/9? What would be a good first step in combining those?
Multiply by one of the reciprocals.
Ooh, multiply by like the reciprocal of the other fraction? I think that would be good if we wanted to divide the first fraction by the second fraction. If we wanted to do something like 1 over 2h plus 9 divided by 1/9, then we could say that's the same as multiplying by the reciprocal of this one, and then multiply straight across. Unfortunately, I don't think that's going to work in this particular situation, mainly just because we're subtracting in the numerator rather than dividing. If this was division, though, then I think this would be a perfect way to do it. So what do we need to do first if we want to be able to somehow combine these two fractions via subtraction?
We need to get a common denominator.
Yeah, we need to get a common denominator. Because in general, you can't add two fractions unless they happen to have the same denominator. Or subtract. So how would we go about finding a common denominator?
You can multiply 1 over 2h plus 9 by 9 on top and bottom, and multiply 1 over 9 by 2h plus 9 on top and bottom.
Okay, so basically, your proposed common denominator that we could find is something like 2h plus 9 times 9. I think that's something that would generally work. If you ever have two fractions, like say 1/3 minus 1/4, a good way to find a common denominator for these two fractions is to just find out what would happen if you multiply the two denominators together, 3 times 4. In this case, we could take, this would be 4 over 3 times 4. This would be 3 over 3 times 4, because here the factors of 4 will cancel out in the top and bottom to give a third. Here, the 3's will cancel out in the top and bottom to give a fourth. And once we have two fractions that have the same denominator, 4/12 minus 3/12, then it's okay to just subtract across the numerator, which would give us something like 1/12. So in general, when we're combining two fractions via subtraction or addition, getting a common denominator is necessary first. And a good common denominator you can always work with is just what's the product of these two denominators. So in this case, one fraction has 2h plus 9 as its denominator. The other has 9 as its denominator. So a good common denominator to work with would be just the product of those two terms. 2h plus 9 times 9. So if we were to do that, in our first fraction, what would go in our numerator if we wanted this first fraction to cancel out to just 1 over 2h plus 9?
Need 9 minus 2h minus 9.
Oh gosh, you're combining it. You're doing everything in a single step. Just this first fraction by itself at first. Sorry.
Oh, it would be 9 over 2h minus 9.
Yeah, or it'd be 9 over this stuff. Yeah, and then, yeah, I think you were skipping right to the next step where we're gonna combine once we get a common denominator for both fractions. But you're absolutely right. Yeah, this first fraction can become 9 over 2h plus 9 times 9. The reason being, these factors of 9 in the top and bottom, we could cancel out if we wanted to just get 1 over 2h plus 9. How about 1/9? What if we wanted to rewrite 1/9 to have a denominator of 2h plus 9 times 9? What would have to go in our numerator here? What?
2h plus 9.
2h plus 9. I like it, because if we canceled out factors of 2h plus 9 in the top and bottom, we'd just be left with 1/9. And this is all over this. Okay, so now I think we can, I'm gonna look at Smug over there. Now I think we can actually combine our two fractions within the numerator of the larger expression. And I think what we'll get when we do that is just going to be 9 minus the quantity 2h plus 9 divided by 2h plus 9 times 9, all divided, of course, by h. Gosh, this divided by h is starting to get pesky. I'm going to make it a little less pesky by just pulling it out. By pulling this h divided by h out in front is just multiplying by a factor of 1 over h. Just to make it a little bit easier to look at and work with. So we don't have fractions within fractions. So what do we get when we simplify the numerator of this expression? 9 minus the quantity 2h plus 9.
-2h.
Yeah, this 9 and this 9 will cancel out, because remember this 9 is being subtracted off via this minus sign. So I think what we'll have left is negative 2h divided by 2h plus 9 times 9. Still don't think we can plug in h equals 0 because we get 0 times 1 over 0. Is there anything we can do to this expression? Make it easier to work with now.
Cancel out the 1 over h with the h in the numerator.
This one?
Yeah.
I like it. We can cancel out this factor of h in the denominator with this factor of h in the numerator. And now we'll have a limit as h goes to 0 of just, well, 1 times. I don't have to, we can just ignore this 1 times. This doesn't do anything. Negative 2 over 2h plus 9 times 9. This is looking a lot better than it did back at this step, I think. What can we do from here?
Plug in 0 for h.
Yeah, I think at this point, if we were to plug in h equals 0, we're no longer going to get division by 0 because of this plus 9 and times 9 term. So now I think we can just plug in h equals 0, and we'll get 0 plus 9 times 9, which is going to come out to 9 times 9, which is 81 in our denominator. And I think that is going to be our final answer. Negative 2 over 81. So this is a bit of an arduous one. I think the key difference between this limit and kind of the limits we were doing on Monday came from the fact that we had a fraction within a fraction, which this whole divided by h, we could treat as just multiplying what I have circled by a factor of 1 over h, which I ended up doing at this step. And then to simplify 1 over 2h plus 9 minus 1/9, we had to combine these two fractions into a single fraction, which became the negative 2h over 2h plus 9 times 9 term. And we combined these by finding a common denominator. In sort of a similar way to how you would find a common denominator if you were to do something like a third minus a fourth. You can just multiply the two denominators together to get something like 12 as a common denominator. Here, our 9 and 2h plus 9, we were able to multiply together in order to give a common denominator of 2h plus 9 times 9. And once we did that, we were able to combine our fractions, and then eventually things were able to simplify out nicely. This h in the big denominator, we could cancel out with a factor of h, and that led us to a number, negative 2 over 81 as our answer. Anybody have any questions, comments, or concerns about this one? For me, I would say this is probably the peak of difficulty that these sort of limit derivatives are going to reach. At least until we do trig functions, but once we get to that point, we'll have a lot more tools to make our lives easier to work with. Great, and with that then, we are done with standard 4. Next up is going to be standard 5. So in standard 5, we're going to be looking at how we can use properties of the derivative in order to make our lives a little bit easier.
Is there another?
Okay, you're not getting that? Yeah. So standard 4, we focused on looking at how do we interpret instantaneous rate of change, or finding the derivative, by taking a limit as h goes to 0 of average rate of change from a point to that point plus h. So in this standard, to start with, I'm going to define the derivative in a slightly different way than how we defined it in standard 4. This time I'm going to define the derivative as being a function of x. And we're going to talk a little bit about, instead of just finding the derivative of a function, let's say f of x equals 1 over 2x plus 3 at a single point, like we did to find the derivative in this last example, we found the slope, the instantaneous rate of change at just a single point. To start off with, in this standard, we're going to talk about how can you find a formula for f prime of x in a way that's going to give us a formula in terms of x that we can just plug numbers into that'll give us an instantaneous rate of change at any point on our graph that we might care to look. So let's see. So to start with, we can say that given a continuous function, f of x, we can define the derivative of f of x which we're going to denote as f prime of x, where f prime of a number x is going to be a function that takes in an x on the graph. So like say, in the last example, we would look at x equals 3. But here, f prime of x is going to be defined to be the instantaneous rate of change of the function f taken at whatever value x that we're looking at. So f prime of 3, find slope at instantaneous rate of change at 3. F prime of negative 10, instantaneous rate of change at negative 10. As we've seen, this is equal to the slope of the tangent line to f, taken at whatever point x. In the formula, we're going to have to calculate this. It's going to be a limit as h goes to 0 of f of x plus h minus f of x, all divided by h. Same formula that we're used to working with back in standard 4, except this time, instead of having just a constant value a showing up in our limit, we're going to leave everything in terms of x. And by doing that, we're going to end up with an expression that, once we simplify whatever this comes out to for whatever function f we're looking at, if this comes out to say something like, I don't know, 2x plus 6, then we should be able to just say, oh, what's f prime of 3? The slope at 3? It's going to be 2 times 3 plus 6. F prime of negative 10? It's going to be 2 times negative 10 plus 6. So let's take a look at an example where we actually are going to have a specific function, f of x. The function I want to look at is going to be 2x squared plus x. And unlike with standard 4, I'm not going to specify where do we want to find instantaneous rate of change. Instead, I want to find a general formula, an f prime of x formula, that we can plug in whatever number we want for x, and will give us an output corresponding. So here, we'll take a little look at our graph of f of x, which is going to be a parabola opening upwards. It's going to look something like that. And so if we want to find the derivative of this function, we're going to need to take a limit as h goes to 0 of f of x plus h minus f of x all over h. And we're going to go through the same process we did in standard 4, but this time we're going to have x's showing up instead of just constant values. So if our f of x is 2x squared plus x, what is f of x plus h going to be? If everywhere we see an x in this expression, we replace that x with an x plus h term. What sort of expression would we get if we replaced our x's here with x plus h's? All right.
2 times x plus h whole squared minus x plus h.
Like that? I'm going to make one slight change. That's it. I think this is a plus, so we'll have 2 times the quantity x plus h squared, replacing this x with an x plus h, and then this plus x becomes a plus x plus h. Yeah, otherwise I think I fully agree with what you have. So that's going to be our f of x plus h term. We're also going to need to subtract off f of x. Well, you know what f of x is, that's just 2x squared plus x. And now, we just have to do what we've done back in standard 4. We're going to do what we've done and multiply this out and simplify as best as we can. So if we multiply out this quadratic, I think we're going to get a 2x squared plus 4xh plus 2h squared. We'll get a plus x plus h minus 2x squared minus x all over h. Get a lovely looking expression here. So, what can we simplify here? I think I see some terms in our numerator that are going to cancel out. Rachel?
The 2x squared and the negative 2x squared. The positive and negative x.
Those are going to cancel? Yeah, the 2x squared minus 2x squared. The plus x and the minus x should cancel out. And so what we're going to end up with is a limit as h goes to 0 of 4xh plus 2h squared plus an h, all divided by h.
Factor out h on top, so it'll be 4x, well, h times 4x plus 2h plus 1 all over h.
Okay, I like it. So all of our terms in the numerator have a factor of h in them, so we can certainly pull out a factor of h from that. Why did you pull out a factor of h? What did
So the bottom and top cancel out, the h's do.
Because this h will cancel out with this h now. And so let's see. What are we going to have left? We're going to have a 4x plus 2h plus 1. And if we take a limit as h goes to 0 of what's left, what is that going to come out to? 4x plus 1. It's going to come out to 4x plus 2 times 0 plus 1, which is going to give us in the end a 4x plus 1 as our final answer. Notice that since we're only taking a limit as h goes to 0, we're not taking a limit as x does anything, only a limit of h. What we're going to end up with is going to be an expression that still has some x's in it. We can plug in 0 for h here, but we can't plug in 0 for x necessarily. And so what we end up with is going to be our f prime of x is going to be a function in terms of the variable x. And so now, if we wanted to find what is, say, f prime of a number like 3, we could just plug in x equals 3 into this expression, and we'll get 4 times 3 plus 1, which is 13. Versus, say, f prime of negative 10 is going to come out to something like 4 times negative 10 plus 1, which will be, what, negative 39? And if you wanted to find the derivative, f prime of x, at a bunch of different points, at several different values of x, having a nice simplified formula like f prime of x equals 4x plus 1 is going to make that a lot easier to do, rather than having to say f prime of 3 is limit as h goes to 0 of f of 3 plus h, blah, 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 and do a limiting quotient like this every single time we wanted to calculate f prime at a new point. So, just for fun, I want to graph what our f prime of x looks like. So f prime of x is 4x plus 1. What type of graph would that produce? Yeah, it's going to be a straight line. Y equals mx plus b. Y equals 4x plus 1. So it's going to have a positive slope of 4, y-intercept of 1, and I think we're going to get a graph that will look something like this. I have to exaggerate this a little bit. Dr. Burstel can draw straight lines. So our f prime of x is going to look something like this. Let's pause for a moment and just see what observations can we make about our function f of x versus f prime of x. Specifically, if we were to look at this value of x right here, where f prime of x equals 0, let's see, that's going to be at x equals negative a fourth, because if I plug in negative 1/4 for x, this will come out to 0. What do you notice about f of x at this point? A parabola, I would argue that our parabola at x equals negative 1/4 is doing something interesting. Yes, Sam?
It goes from decreasing to increasing.
Goes from decreasing to increasing. Specifically, it's going to have a vertex right there, where it's sort of the middle of the parabola, where instead of going down at x equals negative 1/4, looks like that's going to be about where it starts going back up again. If I were to draw it, yes?
I guess I was just wondering because I thought that that represents the slope of a tangent line to that point, and you think that if it was right in between, it would be horizontal, not vertical. Like, how is that line tangent, I guess?
Oh, good question. I would argue we haven't actually drawn the tangent line. Notice that f prime of x doesn't actually give us the tangent line itself. It gives us the slope of the tangent line. So what you just asked is actually a nice lead into my next question. If we were to draw a tangent line to f of x at this vertex, what would that tangent line look like? It would be a flat line. Okay, so our tangent line at this point is going to look something like that. And if we have a flat line like this, what's the slope of that line going to be? It's going to be 0. The same value that we would get if we were to take f prime of negative 1/4. So I think to answer your question, what's kind of the relationship of what's going on between f prime and f here? F prime of x, this line here is not actually a tangent line to f of x. In fact, it doesn't even look like they intersect at all. But if we went to the point on f prime of x at, say, x equals negative a fourth, this point has an output f prime of negative 1/4 equals 0. And that's going to tell us that on our graph of f of x at that point, the tangent line has a slope of 0. And similarly, if we look at, say, a point here where f, we'll call this, I don't know, a half. F prime of a half is going to be a positive number, corresponding to the fact that if we drew a tangent line to our function f of x at negative a half, we're going to get a positive slope. This line goes up as we move from left to right. So ultimately, the relationship between f of x and f prime of x is that at any point on our graph of f of x that we took a tangent line, say at x equals -1/4, where we have a flat tangent line, slope of 0, versus up here, where our slope is positive at x equals 1/2, what f prime of x is going to tell us is how big is the slope of the tangent line at that point. At x equals -1/4, we get a flat tangent line with a slope of 0, corresponding to the fact that our output to f prime of x at -1/4 is 0. At x equals 1/2, f prime is going to be positive, telling us that the tangent line to f of x at that point is going to be positive. And similarly, if we were to look at, say, I don't know, x equals -1, way over here, if I were to draw a tangent line to the graph of f of x at -1, are we going to have a positive or a negative slope there? It's going to be negative because our line is going to be going down as we go from left to right. And that's going to correspond to the fact that if we look at our graph of f prime of x, this line here at -1, f prime of -1 is a negative number. So in general, if f prime of x gives a positive output, that means the original function has a tangent line with a positive slope. It's going to be increasing. And if f prime comes out to something negative, then our original function is going to have a tangent line with a negative slope. And if f prime is 0 exactly, like what's going on at x equals -1/4 here, then the original function is going to have a horizontal tangent line. It's going to kind of have a tangent line that's completely flat, which, if you're looking at a parabola like this f of x, comes from having a vertex to your parabola. Any questions, comments, concerns relating to f of x versus f prime of x graphically?
Does this apply for like all kinds of functions? Because like this has like a neat like parabola, but what if like I don't know the names for the different functions, but with some of like the other functions we've looked at where it doesn't have like a neat parabola.
Sure. So like something with a bit more curve, with a bit more wackiness to it?
Yeah, or only that curve, that only curves one way or something.
Sure. So if we were to look at another example, like let's say we had a function, I don't know, f of x that did something like this. This is our f of x. Even without a formula for f of x, I could probably say that f of x, I could see two different points where f of x is going to have a horizontal tangent line, specifically at here and here, which is going to tell us that at those 2 points, our derivative is going to be 0. And I could even try and guess what this is going to look like. I would say something like this, where our function has negative tangent lines up to here, so our derivative should be negative up to this point. Positive tangent lines from, I'll call this point A and this point B. Positive sloped tangent lines from points between A and B. And then to the right of B, our tangent lines start having negative slope again. And so the answer ends up becoming, yeah, you absolutely can tell some graphical relationship between f of x and f prime of x for all sorts of functions, which is going to be a big part of standards like 13 through 16, I think, is going to be all about how can we actually, if we know some information about f prime of x, how can we use that to help us graph f of x? There's one key word that I am going to point out that is necessary to have f prime of x and be able to do this sort of process. and that's that the function needs to be continuous for reasons that we're going to see. If our function's not continuous, then our derivative ends up breaking down and we won't be able to do it very easily. Which is why I wanted to talk about continuity back in Standard 3. One of the reasons is because you need continuity to be able to do this derivative taking process. Any other questions or comments? Okay, we have finally come to the point that you've all been waiting for. How do we take derivatives without having to do the limit as h goes to 0 of nasty difference quotient every time? So the rest of Standard 5 is going to be about looking at different sorts of shortcut techniques, some theorems and results that are going to allow us to take derivatives of something like 2x squared plus x much easier. So here's what I promise you. By the end of Standard 5, you'll be able to take this derivative in 1 or 2 lines, instead of taking it through a whole board's worth of space. So let's go through and look at some of the results that are going to allow us to do this. So first result I want to look at is going to be called the power rule, which is arguably the most useful of the different derivative taking techniques we're going to look at. And what the power rule says is that if f of x is some power of x, like x squared, x cubed, x to the 10th, x to the 1.5 power, if f of x equals x to the n, then the derivative, f prime of x, is going to be equal to n times x to the n minus 1. Simple as that. In order to take a derivative of x to some power, you pull the power n down in front of the x, and then you subtract 1 from your exponent. So let's take a look at a few examples. Let's say our f of x is x cubed, meaning our n in this case is going to be equal to 3. What would we get if we used the power rule to differentiate f prime of x? What's it?
3x squared.
So you pulled the 3 down in front and subtracted 1 to get 3x squared? I like it. Boom, one line. No need to take limit as h goes to 0 of x plus h quantity cubed minus x cubed all over h. Power rule says, nah, you don't need to do any of that. Pull down the exponent, give us a 3 out in front, and then subtract 1 from it to get x squared now. Square root function. That was one we saw towards the end of Standard 4 that involved having to multiply by some fancy square root expressions in order to calculate the derivative of a square root expression going on. All right.
You could rewrite it as x to the 1/2.
Okay. You can certainly do that. Is that helpful?
Yeah, because then we can just like use 1/2 as n. So 1/2 times x to the negative 1/2.
Like that? What do y'all think? Sounds pretty solid to me. Square root of x, as written, is not something that looks like you can use the power rule. But if you rewrite that as x to the 1/2, you rewrite that as x to a fractional exponent, then there's certainly no reason why you couldn't just multiply by a half and then subtract 1 to get 1/2 x to the negative 1/2. Dr. Gerstle doesn't like negative fractional exponents. So is there any way that we could rewrite this expression in a way that'll sort of avoid having a negative x to the negative 1/2, which is kind of scary to work with? Yeah, just
You put it in the denominator, then it turns it back to positive.
okay. So we could write this as 1 over 2x to the positive 1/2.
Yes.
Sounds good. Yeah. We can use the fact that x to any negative power is the same as 1 over x to that positive power to take x to the negative 1/2 and rewrite it as an x to the positive 1/2 in our denominator.
So when you say you don't like leaving it like that, if we had a problem like that on a quiz, would you count it against us if we left it in the top form?
I'll answer that in just a second. I want to kind of, because I'm still not happy with this answer. Yeah, I'll address that once we get to the end. I like how our original function had a square root in it. Our original expression didn't have any fractional exponents to it at all. How about we rewrite 1 over 2x to the 1/2 so it doesn't have any fractional exponents showing up? You know?
1 over 2 square root of x.
Yeah, we can do sort of what Riley did earlier, but in reverse, and rewrite this x to the 1/2 as just a square root of x. And this is my favorite form of the answer.
I'm really missing something here. I have no idea why, but why is the 1/2, the 1/2 x become 2x when we take the
As we go from here to here, why does this 2x appear in the denominator?
Yeah.
I would say because I'm going to add a step in right here. If we rewrite x to the negative 1/2 as being 1 over x to the positive 1/2, then when you multiply these two sort of fractional expressions together, the denominators will combine to give you a 2x to the 1/2 in our denominator.
I was just missing that. I appreciate it.
Yeah, no problem. Yeah, no problem. I'm glad you stopped me to ask that. So, question is asked. If I were to ask on a quiz, say, g of x equals square root of x, is this an acceptable answer? Or is this an acceptable answer? And in general, I would say all of those answers are fine. Unless I explicitly say otherwise. Unless I explicitly say something like, simplify your answer. Or leave your answer in the same form, in the same general form as the original function. Then you would have to do something like this. I like this answer the best. Specifically because if I were to ask you to evaluate this expression at, say, a number, like say at x equals 9, if you were to ask me, what is 1/2 times 9 to the negative 1/2, I'd be like, 9 to the negative 1/2. I don't know what that is. Whereas something like 1 over 2 square root of 9, I'd be like, oh, square root of 9 is 3, 2 times 3 is 6, it comes out to a 6. So I think this expression is generally the easiest to work with, which is why I recommend you get in the habit of rewriting in the original form like this. But since these are technically all equal, I would not count it against you if you didn't, unless I told you otherwise.
So you don't care if we have a square root in the denominator?
Oh my gosh, we have a square root in the denominator. Oh, dear. If you want to multiply top and bottom by square root of x to get square root of x over 2x, that would be another acceptable answer. Personally, I'll say I really don't care about square roots in the denominator because, I mean, plug in the number for x. I don't think either one of these is any easier or harder to plug in x for. X equals 9, it comes out to a 6. X equals 9, it comes out to 3/18, which simplifies down to a 6. all of these are acceptable answers. No need to rationalize your denominators in this class because I frankly understood the point of rationalizing the denominator much anyways. Let's do one more example before we move on. How can we use the power rule to help us take the derivative of 1 over x? Zach?
Well, first you want to rewrite it as x to the negative 1. Then you go do the power rule.
Okay, so what is the power rule going to give us?
Negative x to the negative 2.
Negative 1 times x to the negative 2. And are you happy with that answer?
I mean, I would be, but you're not going to be, so it'll just be negative 1
Darn
over x
Skippy.
squared.
Yeah. Again, this answer is perfectly fine. And same rules as I said, if you were to answer that on a quiz, I would probably draw a frowny face next to it, but give you full credit for it. But I like this. I don't like my negative exponents. I like answers like this, where if I were to plug in a number like, say, x equals 3, what's 3 to the negative 2? I would have to stop and kind of think about that. Whereas negative 1 over 3 squared, oh, that's negative 1. All right. We're out of time for today. On Friday, we're going to continue our discussion of Standard 5. At the start of class on Friday, though, I'm going to do something you likely haven't seen before, even if you've taken a calc course. I'm going to talk about why the why the power rule is true. Specifically, give some explanation for why does this seemingly magical derivative taking technique work out as nicely as it does. So that'll be it for today. Hope you all have a good rest of your day, and I will see you all on Friday.